Our next talk will be by Jeffrey Meyer, who's going to talk about equivariant trisections.
All right. Thanks for the introduction, Dan. Very special thanks to Dave and Delphine for organizing this fantastic conference and the wonderful mini courses we had last week. And thanks to CERM for hosting this conference and the mini courses last week. It's really wonderful to be here in Lumini in the Calanques doing topology. So today I want to tell you about some joint work with Evan Scott on equivariant trisections. So trisections have been around for, I guess, at least a decade at this point, depending on whether you go off the archive date or the... Oh, it does that, yeah, okay. Depending on whether you go off the archive date or the published date. And for a long time, there was this question of, okay, well, if you have a four-manifold, you can put a trisection on it. If you have a finite group action on that four-manifold, is there some way to build the trisection theory so that it's compatible with the finite group action? And that's what we did, and that's what I'm going to talk about today. So these are, all the pictures on the board are, except for the fish-looking one, all the pictures on the board are equivariant trisections. Any questions? Okay. All right, let's start off with the definition, and then we'll unpack. We'll unpack any terms that come up that we're not happy with. So fortunately, Evan talked a little bit about a special class of finite group actions on four manifolds called linearly parted actions. And Evan drew a picture very similar to this one, and this is, oh, these are, okay. So exercise, figure out which chalk strokes are missing from the board. There's at least one chalk stroke missing, so okay, probably more. So what's the setup? So X is going to be a four manifold. With an effective G action for some finite group G. So what I mean by this is that, yeah, so already, like, okay, what do I mean by this? I mean that we have an embedding of G into the orientation-preserving diffeomorphisms of the manifold. So in particular, every element of G acts smoothly as a diffeomorphism. Stay. Okay. All right, so a G equivariant trisection. T of X is a decomposition. So first of all, it's a trisection. So, but I'll talk. I mean, I won't just assume that everyone's comfortable with the idea of a trisection, a decomposition. So, you know, we cut our manifold up into three pieces. With some properties such that for all indices, which I like to consider cyclically, we have some properties. Okay, so let's see if I have room to do it here. Okay, so the first condition is that the pieces x1, x2, and x3 are going to be four-dimensional one-handle bodies, and the induced G action is going to be linearly parted. Okay, so xi is congruent to the boundary connected sum of some number of copies of S1 cross B3. And the induced action of G, oh, I left out an important word. Let's add it right here. Is invariant, so we'll require that the the action of G preserve the sectors setwise. So the induced action of G on xi is linearly parted. Okay, so and I think I will go ahead and draw the, so close, the obligatory schematic and just sort of fill in. I mostly like to draw this just to keep track of indices, or to the indexing conventions, and also to establish the color conventions. So let's say this is going to be, I guess we're not there. This is going to be H1. Let's say this is going to be H2. This is going to be H3. Yet to be defined. So the three pieces show up like this, and then in the middle we're going to have our surface sigma. So, okay, so carrying on, and so each of these pieces of the trisection are invariant four-dimensional one-handle bodies, and the induced action has to be linearly parted. So this is something that we'll need to say a little bit about. It's a very important hypothesis that sort of lets the entire theory get off the ground. So the second condition is the condition on the pairwise intersections. So the intersection of any sector with the next is an invariant boundary connected sum of G copies of the solid torus. So this is a three-dimensional handle body of genus G. So for example, this guy over here, sort of pictured, is, what is it, 3? Okay. 3 copies of S1 cross D2. Maybe just for people whose mind is just wandering all over the place, the blue and the red in this picture don't behave in the same way as the blue and the red everywhere else. Okay. So this picture sort of lives in isolation from everything else. And then the third condition is that the boundary of the HI, which also happens to be the common intersection of the three pieces, is a closed genus G surface. Okay, and then one important thing is that the union H2, H3, this is called the spine of the trisection. And the complexity of the trisection, which sometimes is worth thinking about, is the tuple G, K1, K2, K3. So this is the genus of the central surface and the number of one handles in each of the four-dimensional one handle bodies. Okay, so any questions about the definition here so far?
You're going to remind them of linearly parted.
Yeah, let's go ahead and do that next. Okay. So what does it mean for xi to be linearly parted? So xi, let's say, is linearly parted if there exists a collection B in xi of neatly embedded three balls such that xi cut open along the three balls is a bunch of four balls, technical term. And for each four ball in this sort of bunch, the induced action is linear. Okay. Say that again, please. Yeah, I've been saying induced action. I think I mean stabilizer, yeah. That's right.
Oh, already there. You were allowing actually the xi to permutate.
No. The xi cannot be permuted amongst themselves. They are invariant.
But the balls are not necessarily invariant.
Oh, but the balls are not necessarily. Okay, yeah, so this is why we're doing this. All right. Okay, so it's really useful. This is the definition for a four-dimensional one-handle body equipped with a g action. So there's always a g action in the background, even if I sort of forget to say it explicitly. This is what it means for the sort of like action to be linear parted. If we go down a dimension, so what's going on here? So this is a genus three-dimensional one-handle body. And as Evan sort of described, the group here that's acting is the dihedral group D3. And the action is, imagine this thing was just literally made out of metal, and D3 is acting by the physical transformations of this metal object, this rigid metal object, assuming it's equilateral and regular and all of that stuff. And so what we see is that the red disks, so the red disks are playing the role of the ball system. Okay, so in this one lower dimensional example, the balls are not three balls, but they're two disks, and they're cutting the genus 3 handle body up into a bunch of three balls, and on each three ball, the induced action is linear, right? So for example, let's play with some three balls. So if you look at this center three ball here, it is left invariant setwise by the entire action. So there's sort of the flip here, all the flips and the rotations all fix this. So the stabilizer here is D3, which is a linear action on the three ball. In contrast, this one is sort of permuted by this outer one, or maybe even the next to outer one. Those are permuted around cyclically, so their stabilizer is Z2 coming from one of the reflections. Again, that's a linear action. So what happens in dimension 3 is that finite group actions on three-dimensional handle bodies are always linearly parted. Okay. So this is maybe I'll write that. It's sort of important. If you get bored, you can try to prove this. It's an exercise. I'm joking. It involves the equivariant disk theorem, the Smith conjecture, and the Poincare conjecture. Okay. So finite actions on three-dimensional handle bodies are always linearly parted, meaning I can find a linear parting ball system. Linear is that the induced action on each piece that you cut it open is linear. So like arising from SO in SO4 or SO5 or yeah.
But you can embed it?
Conjugate. It's conjugate to an orthogonal action.
Okay, so it's a ball sitting inside.
It's a ball, exactly. Yeah, exactly. Yeah, if you identify it with the unit ball, then you.
From a subgroup finite
Yes,
subgroup
a finite subgroup of SO whatever. Yeah, good question. And so the question was, what does linear mean? Yeah, let me come back to that because I haven't introduced that yet.
I forgot to remind you to repeat the question.
Yes. Yeah, I remembered after I answered it. Yeah. Okay. Yell at me if I forget again, please.
I have a question.
Okay.
The balls that cut up each xi and make it linearly parted, do they have anything to do with each other when xi meets xi plus 1? You know,
Oh yeah, that's a good question. they probably intersect in very complicated ways. Yeah. The question was, I have the linear parting balls in, say, x1 and x2. And the boundary is a collection of spheres in the boundary S1 cross S2. And so I have spheres in this one, S1 cross S2, and spheres in this S1 cross S2. They crash through each other. Yeah, good question. OK, so like I said, this is actually attributed to the equivariant disk theorem of Meeks and Yau, followed by the Smith conjecture, which involved many mathematicians, including Thurston, and also the three-dimensional Poincare conjecture, which settled the spherical space-form conjecture of Perelman. So everything's easy in dimension 3 if you are follow in the footsteps of all of those great mathematicians that did all that work for you. So maybe this is a motivation for why this is a reasonable guess at to what structure we should have here. But there's actually an even better reason why we need to require linearly parted, which, oh yeah, so how do I want to get to this? I'll write some theorems, and then I'll get back to why we want things to be linear parted. Okay, you know what linear parted is. We can worry about why later. Okay. So I planned roughly as much material for this talk as I did for my 4-lecture mini course last week. So I don't know where this is going to go, but if you ask questions, then that's where it will go. Okay, theorems. Actually, maybe I'll just make one more caveat for now. If S in X is a collection of invariant surfaces, then we can assume T bridge trisects each member of S. So there is this sort of awkward aspect to this material where it's all a little bit verbose to present, and then you present it for the 4-manifold picture, and then you have to go back and redo everything again with little tweaks to account for a codimension 2 surface. So this is the move from trisection to bridge trisection. Everything works out perfectly well. It has to do with what Gordon was asking about the blue disks. So the blue disks up there are invariant bridge disks for an invariant boundary parallel tangle. And you can go up a dimension and talk about, if you know about bridge trisections, you've got these trivial disks in the sectors. If they're invariant, you can ask them to have invariant boundary parallelizing three balls, which you can ask to be disjoint from B. So notice blue and red are disjoint, in which case you have something that you can define to be an equivariant bridge trisection or an equivariant bridge trisected position, and everything works fine. I think I might stick with writing things about 4 manifolds and saying things out loud about how it carries over to codimension 2 surfaces. But feel free to ask anything along those lines. Okay. Right, so we have some theorems. Okay. Again, all of this is joint with, oh yeah, that's right, okay. All right, all of this is joined with Evan Scott, and it's spread over 2 papers. So the first paper, I'm kind of spoiling a little bit what's to come, but the first paper, which ended up being split out, establishes an equivariant version of Laudenbach-Poinarou, which may be of independent interest, and the second paper sort of fleshes out all the details of the theory of equivariant trisections and bridge trisections. Okay, so the first theorem I'm going to write is that these things always exist. Oh yes, I already got kind of out of order. Okay, sorry. I just need to start writing and stop blathering. Okay, so first theorem is that equivariant bridge trisections always exist. Meaning I can go from a 4-manifold equipped with a finite group action, equipped with a collection of invariant codimension 2 surfaces, and I can find a trisection for that 4-manifold that satisfies the definition of a G-equivariant trisection, such that the invariant surfaces are in bridge trisected position. And then I think what makes the theory of trisections interesting is that once you put your 4-manifold into this rigid structure, you can throw away the 4-dimensional pieces and just worry about the spine. That's why the spine is such an important part of the definition of a trisection, because it determines the topology of a trisection by Laudenbach-Pointerou rule. And so one of our theorems is that the same is true in the equivariant setting. So equivariant bridge trisections are determined by their spine. By their spines. Okay. And the input for this is the equivariant Laudenbach-Pointerou theorem. Which maybe I'll write out somewhat explicitly. Okay, well, we're getting somewhere. All right. What am I trying to write here? Okay, so what is the idea of this theorem? So we're going to let G act on a 3-manifold Y, which is a connected sum of S1 cross S2s. And then I'm gonna rope in the codimension 2 business here. So we're gonna let U in Y be an invariant unlink. Okay, and we're going to let x1 d1 and x2 d2 be, what did I write here? I just wrote equivariant filling, so okay, let's go with that. Equivariant fillings of y comma u. What does that mean? These are pairs, these are 4-dimensional one-handle bodies. So each of these looks like, oh yeah, so what's the right way to write this? Let's write it like this. Let's write it as, let's try it like this. F comma P cross D2, where this is a compact surface with boundary. This is some points, and we cross it with D2. So if you take a compact surface with boundary, any compact surface with boundary, and any collection of points in it, and you cross with I, you get a 3-dimensional handle body with a bunch of trivial, with a trivial tangle in it. Okay? If you cross with I again, you get what we usually call like a trivial disk tangle or a trivial disk system or something like that. And the 3-dimensional handle body being crossed with I once again becomes a 4-dimensional one-handle body. So this is to say that each of these are 4-dimensional one-handle bodies, and each of the Ds are neatly embedded boundary parallel collections of disks. And the fact that they're equivariant fillings means they admit G actions that restrict to the boundary Y as the given G action. Okay. Then x1 d1 and x2 d2 are equivariantly diffeomorphic. So this just means there's a diffeomorphism between them that respects the G action. It takes one G action. Oh, that's false. False. Theorem's false. Evan, you can tell me whether the theorem's false, or you're going to tell me I made some other mistake. That's the one. Okay. Yeah, the whole point of everything. Oh, that's what it means to be an equivariant filling, though, right? Okay. Okay, so it's really important here that it's linearly parted. Okay. It's actually demonstrably false without the linearly parted condition, as maybe I'll explain in a minute, and it's true with it. So that makes it an important part of the thing. Also, I guess, equivariant, linearly parted equivariant fillings always exist. So given this y, I can always fill it by a G equivariant four-dimensional one-handle body that's linearly parted, and if I fill it in two different ways, they're G diffeomorphic. Okay, so this is what you want for a Laudenbach-Pointerou theorem in the setting of equivariant four-manifold topology. Okay. Yes? Yeah, there's a diffeomorphism that respects the G actions. Oh yeah, good. Thank you. That's definitely in the notes. Not that that matters to anyone here. Okay, equivariant diffeomorphic REL boundary. Thank you, Evan. This is like a little snapshot of our collaboration. Okay. Okay, so I think I've mentioned a couple times that this linearly parted stuff is really important, so maybe I'll just finish by saying this, right? So there exist, so Evan mentioned an action on V4 is linearly parted if and only if it's linear. So for the 4-ball, there's no difference between linearly parted and linear. And then the second fact, so maybe I should be a little bit clear here. This is our theorem, and then a theorem that's not due to us. So this is, as Evan mentioned, you can attribute this first to Giffen, and then to Gordon. Giffen gave the first examples. Gordon handled gave more examples in more generality. There exist nonlinear actions on V4. Okay. So this is what is not true from all these big theorems in, so in particular the Smith conjecture, which says that every finite group action on the 3-sphere with a fixed point has an unknotted fixed point set. Or cyclic, every cyclic action. That's demonstrably false in V4, and I actually drew a picture of it here because Evan promised a bottle of pasties to whoever could come up with a handle diagram for a nonlinear action on V4 during his lightning talk. Is that right? Okay, good. Well, here you go. What I've drawn here is, so this is what's the action? Oh yeah, Evan told me I need to draw the action. So the action here is the skewer, and rotate. So this is a Z2 action. So in this example, G is Z2. The trisected manifold here is the double branch cover of, what was the notation for twist spun? Was it twist? This is the 3 twist spin of the 3-2 torus knot. 3 twist spin, 3 twist spin, double branch cover. And by a theorem of, actually, this is actually due to Deborah Goldsmith and Kaufman. This is actually diffeomorphic to S4. Okay? So this is a genus 3. So maybe just some more aspects of this, since I haven't really discussed an example of a trisection or example of yeah, let's just kind of like drill down on this. You know, the other thing that would take me another 20 minutes to really dive into in detail would be to talk about diagrams. So let me just come back over here. Sorry, I'm a little all over the place, but it's all going to be on the board at the end of the lecture. So in the classical theory of trisections are determined by their spines, spines are determined by, the spines are made up of handle bodies. I mentioned this in the mini course. Handle bodies are determined by cut systems of curves. If you just look at those curves, those give you what's known as a trisection diagram. Similarly, if you have a trivial tangle in the picture, the trivial tangle is determined by some shadows, or disk bottoms, as Sashka likes to call them, on the boundary of the surface. And so you get something called a shadow diagram, or I guess, well, let's just call them shadow diagrams. Okay, yeah, that was enough of a homage to disk bottoms for one talk. Equivariant bridge trisections are determined by their spines. So the theorem to write here, I think, is that equivariant bridge trisections have shadow diagrams. I guess maybe you would call these invariant shadow diagrams or something. This is actually what I've drawn all over the board, right? I've drawn invariant shadow diagrams all over the board. So we have equivariant bridge trisections always have invariant shadow diagrams, or if you just want to think about four manifolds, equivariant trisections always have invariant trisection diagrams. And equivariant, now I'm all over the place. Equivariant shadow diagrams determine equivariant bridge trisections. Okay. So, for example, let's go and actually let's pay a little bit of attention to this. So, since this is here we see that our central surface sigma has genus 3. Okay, so that means to build my three handle bodies H1, H2, and H3, I need to give you three curves of each color. And these three curves, being linearly independent in homology, will build out three handle bodies. That will give me the spine of my trisection, and once I have the spine of the trisection, I'm done because of, well, Lautenbach pointer or equivariant Lautenbach pointer. So the first red curve is purple, and it's also the first blue curve. That's why it's purple. The other two red curves are here, alpha 2, alpha 3. The other two blue curves are here, beta 2, beta 3. The green curves are sort of variously colored in green. Maybe this is gamma 1. I think there's another green one here. This would be gamma 2 here, and it's probably a little bit hard to see. And then there's actually a yellow, which may or may not look any different than the two green curves. We'll call that gamma 3. Okay. And the key idea is that the entire diagram is invariant under this hyperelliptic involution. Okay? And the hyperelliptic involution, I probably won't get to say this, but we have a theorem that characterizes hyperelliptic trisections in terms of the quotient being S4. I don't think I'll say any more about that. But the point is, the quotient of this is actually S4 again, and the quotient of the fixed point set is this twist-spun 2-knot. And so this is actually the twofold branch cover of the twist-spun 2-knot. By Goldsmith and Kaufman, it's S4 again, which means the Z2 action is an involution of S4 whose fixed point set is knotted. So it can't be the standard linear action, linear involution of S4, otherwise the fixed point set would be unknotted. And there's sort of a well-established way to go from a trisection diagram to a Kirby diagram. And if you have an equivariant or invariant trisection diagram, then you get an invariant Kirby diagram or handle body diagram. And so Evan implored me to draw the axis here. So it sort of passes through here. Yeah, he was also giving me a hard time for that it wasn't very symmetric, but I thought that was unjustified. Okay. So you'll notice it intersects sort of the attaching curve for each handle in 2 points, and it involutes them all, it folds all the handles in I can't actually show, well, I mean, I have been unable in the last 24 hours to show directly that either of these correspond to S4. And it's, so, you know, Alex and I have drawn these pictures previously, and what's interesting about this is these give rise to interesting genus 3 trisections of S4. And, you know, conjecturally, every trisection of S4 is stabilized, but these don't appear to be stabilized. So if you can find a state that, if you can convert this to a trisection that's stabilized, or even if you can turn this, show that this is S4, I'd be interested to see how that works. I think it's probably challenging. Okay. All right. I think we're doing okay. Any questions about this? So this is a counterexample to the 4-dimensional Smith conjecture. It's a purple one handle. So I guess I didn't finish saying this about the, what's that? No. So in this example, all of the complexities of the, so it's a 3-1 trisection. All the complexities are 1. The yellow, this is supposed to be yellow, and it's a 0-frame 2-handle that links the 1 handle twice. And this is a 3-framed 2-handle that links the 1 handle 3 times. So at least homologically, it's the right picture. Yeah, and they link once here. Oh, and there's a 3-handle, yeah. Do we say that? Yeah, it's been a long time since I've drawn a Kirby diagram and not a trisection diagram. We could say there's a 3-handle hiding up above, and a 4-handle too. The horizontal axis, this is the fixed point set of the group action. The 1 handle is the purple dotted curve that kind of runs around the outside. It's the common alpha 1, beta 1 on the surface is where the purple thing came from. Yeah, where did this come from? I mean, just quickly, like, I can take gamma 2, or what did I take? I took gamma 1 and gamma 3. They each are dualized by these beta curves, and so I can kind of push them off the surface into the beta handle body, and they give rise to these two curves. So, I mean, this is something people ask. Oh, yeah, sorry. I feel like every talk that has a Kirby diagram in it, like somebody gets asked to draw the dot bigger. Okay. Oh, I thought about that, yeah. Good joke. Okay, yeah. Now it's invariant. Okay.
Can I ask a stupid question?
Yeah?
What is the standard action of U2 on S4, the standard linear?
Rotation, like it's this. So rotate through pi, and then cross with D2. Oh, you're talking about S4? I guess you suspend that then. Is that right? Is that saying the right thing? This is an action. This would be the action on B4, right? So so here's a Z2 action on the disk. I just rotate through pi. If I cross with D2, that's an action on the 4 ball. So you think of.
That is 0.5 D2, okay.
Yeah. So disk times D2 is B. So this gives B4 D2. So the fixed point set of rotation of the 4 ball is a disk. You know, it's this. In between, it's this picture. Maybe this is a better way to draw it. So here's B3 D1, and then I cross with I. Would be another way to do it. You can build everything up from the bottom. Okay. Yes?
Another way to see this would be saying, like, have an order 2 element of SO5 back on S4, right?
Yeah, that's what I mean by linear. That's what I mean by a linear Z2 action. Yep. An order 2 element of SO5. Yeah. Okay. There's a fixed point free one, that's right. There's a fixed point free one. But that wouldn't give a manifold downstairs. And that's something you kind of have to be really careful about, and we spend sort of many pages dipping in and out of that. Okay, I don't know what. There's some more stuff there. Okay. Let's see, what should we do next? So maybe some Yeah, I mean, okay, so I drew some pictures. Do you guys want me to talk about some of these pictures, or do you want me to say some general consequences of the theory? Audience participation. Pictures, okay. Okay, so let's talk about this picture here. So this is a genus 2. This is a genus 2 surface. So it's a 2-0 trisection diagram. I mean, how do you know? Like, so it's genus 2, so there's a 2 here. And then if you look at the pairs of curves, red, blue, blue, green, green, red, they all give Heegard diagrams for S3. So that tells you that along the spine, all 3 of the unions of the handle bodies are 3 spheres, which tells you that the sectors are 4 balls. Okay, so what manifold is this? I guess there's not really enough information. I haven't really given you enough information to answer that question. Some people know what it is. I could play the same trick I played with pushing off my Kirby diagrams. I could play that same trick to get a Kirby diagram here. These are not Legendrine. Are they? Okay. Is the TV right? Okay. Okay. All right. So anyway, this is a picture of S2 cross S2. Okay. And okay, so here's the question. What does it look like the group is? If I told you this was an equivariant diagram, what would the group be? Z2? Klein 4 groupa? Yeah, groupa. Yeah, it's actually, it is Z2. There's a hyperelliptic involution. There's a rotational involution here, and there's a rotational involution here. And so it's actually sort of the maximal symmetry of this picture is Z2 plus Z2. And we can study what the quotients of this action are. So let's see. What colors do I want to use? I was gonna write out what these maps are in coordinates. So let's maybe go ahead and do that. Okay, let's talk about involutions of S2 cross S2. So one of the things I've loved about doing trisections for the last however many years is that they've given me a lens to approach classical things that topologists have understood for half a century or longer, and kind of see them with pictures, which helps my brain. But so here's just some simple involutions of S2 cross S2 in coordinates. Okay, so we're gonna think of S2 cross S2 as we're going to put cylindrical coordinates on each component. Okay. And using these coordinates, I can describe some maps. So that the first map is tau, and how does tau act? It acts by negating the 2 theta coordinates. And in this trisection, this is sort of non-obvious. I think you're just going to have to, given the amount of time we have left, you're just going to have to sort of trust me on this, although we do spell out all the details in the paper in the sort of extended analysis. So if you want to check that out, the axis of rotation for tau is this one here. Okay. So tau is tau, which is the sort of negation of the 2 angular coordinates, ends up being hyperelliptic involution of this surface, and this is the quotient if you mod out by tau. So tau generates a Z2, and if you mod out, you get this. In fact, we have a theorem that says because tau is acting in a nice enough way, we know we're always going to get a trisected manifold in the quotient. And in this case, we get a genus 0 manifold, and so it has to be S4. And the fixed point set of tau ends up being a torus. So the quotient here is S4 comma T2, where T2 is the unknotted torus in S4. Okay. Let's do another one. Let's do rho, I think. Yeah, let's do rho. So what does rho do? Rho swaps the angular coordinates. And it swaps everything. It swaps the two S2 factors, sorry. Rho swaps the S2 factors. Okay. And how does rho show up in this picture? It's the rotation that's like rotation about the z-axis here. So this is rho. And the quotient is here. And there's just some fun things here, right? So for example, the fixed point set of rho ends up being the element 1, 1 in not enough room. Slightly more room. Okay. Fixed point set of rho in homology is the 1, 1 element in Z2, which is the second homology of S2 cross S2. So it's the sort of diagonal sphere in S2 cross S2. And its fixed point set down here, this is what the fixed point set looks like in terms of these, in terms of the quotient. And what we see here is actually, this is a doubly pointed, so this is a doubly pointed trisection diagram for the total space, which is CP2. This is the genus 1 trisection diagram of CP2. So right away you see that the quotient of S2 cross S2 obtained by swapping the two spheres gives CP2. And the branching locus of this action, the image of the fixed point set, is the degree 2 curve, the conic in CP2. And now if you compose, let's see, what's the fastest way to do this? The fastest way to do this is to say let this thing, what is it, eta? Eta be the composition of tau and rho, which I guess you can figure out what that does. Eta is this guy, pi rotation of the figure this way, and its quotient is down here, quotient out by eta, and this is CP2 bar, C2 bar. So it's the mirror of this. Oh, and the fixed point set is like right here. It's like a point on the top of the surface and a point on the bottom of the surface. And again, this is a doubly pointed, so this is a doubly pointed trisection diagram for this pair. And the fixed point set of eta is the other diagonal, 1 minus 1. Class in homology is 1 minus 1. So you can kind of see like just a lot of really interesting objects with this one sort of equivariant trisection diagram. You can also see, for example, if I track tau down through rho, right? So I have a Z2 cross Z2 action. If I do one of them, then I still have one of them to be done here. So maybe you call this like tau star or something, the quotient action of tau star. This is hyperelliptic involution of this diagram. It turns out this is complex conjugation on CP2. Complex conjugation on CP2, and the quotient is S4. So I mean, this was actually like a major theorem. Okay, Evan, you got to help me. So the major theorem of Massey and Kuipers from like the 70s or something, where they showed that CP2 quotient out by complex conjugation is S4. Okay, but you can actually give like a really straightforward and beautiful proof using like the moment map on CP2 and trisections. That's like much easier than 1960s coordinate topology. How are we doing? Okay. Any questions? I don't think any questions about all that? At this point, that's just like a gratuitous picture. I mean, I guess it's interesting, but maybe I should at least say what it. Should I say what it is? I'll save that. Let me say some more general nonsense first. Okay, some kind of interesting things that came up while we were doing this. So, okay, I'm going to try to state this theorem rather precisely because it's a little confusing. So, let's let T be a G equivariant trisection of X, and let's let N be a normal subgroup of G. Then the following are equivalent. One, the first thing is that if we quotient out X by this normal subgroup N, and this admits, so first thing that could happen, the quotient admits a smooth structure, making it a G mod N manifold. Okay, I didn't really introduce this terminology. A G mod N manifold is a 4-manifold with a G mod N action. So that is equivalent to the quotient of the trisection is a G mod N equivariant trisection of the quotient. And all of this happens if and only if the stabilizer of N of every point acts as a rotation group on the neighborhood of X for all X in X. Okay, so this gives like and actually these conditions can also be verified from the trisection diagram. So there's basically trisections and trisection diagrams are telling you something about the existence of smooth structures on the quotient. And one of the reasons that this is most interesting is that apparently there's this kind of open question in equivariant topology, which is that this is, I guess, an unknown fact. Those are just letters. Okay. It is unknown whether X mod N may admit multiple smooth structures compatible with the map from X to X mod N. Okay. So you might think that if you have a smooth 4-manifold and you have a reasonably nice action on it, that you get like sort of a unique or canonical smooth structure on the quotient. But this isn't even known. It could be that you get that there are different smooth structures on the quotient manifold that are all compatible with the quotient map. But what this tells us is that those different smooth structures might somehow be detected by the different equivariant trisections that you can put on the manifold X upstairs. So equivariant trisections on X might be telling us something about different smooth structures on the quotient manifold. This just seems like a very weird kind of basic differential topology problem that is apparently very challenging and not known. Okay, a couple minutes left. Any questions? Yes? So that the quotient map is smooth and continuous. Mm-hmm.
We've
Sorry.
seen 2 different N actions.
No, I think for the same action.
I just have one map from X.
Yeah, so basically it's easy to tell whether this is a topological manifold and that it admits a smooth structure. But whether it could admit other smooth structures that, I guess, pull back to the same smooth structure upstairs is apparently not even known. And so did they figure it out in the Z mod 2 case?
They did figure out.
Okay, and who's they, remind me?
Hamilton.
Hamilton. Hambleton. Yeah. and someone else. Yeah, so they have an appendix in one of their papers that talks like just about the Zmod 2 case, and it's yeah. I understood all of it. Okay. All right, last bit here. Two theorems to finish off, I think. Oh, now I can come over to this picture. Yeah. Okay, so so the first theorem is, so I'm sort of paraphrasing here. It's that genus 1 equivariant trisections are geometric. Okay? And what we really mean by this is we mean that if G is 1, then the group is living in one of these sort of automorphism groups. Like if it's a trisection of the 4 sphere, it's living in SO5. If it's a trisection of CP2, it's living in PU3. If it's a trisection of S1 cross S3, it's living in SO2 cross SO4. Okay, so you can only have very rigid actions on that leave invariant of genus 1 trisection. And then maybe I'll finish with a conjecture, which we just weren't quite able to prove, and so it's not in the paper, the result's not in the paper, but I think I want to phrase it as there are only, I don't quite know how I want to say this. So this is paraphrasing. Okay, let's write it like this. There are only a few equivariant G equals 2 trisections. Okay, so these are some of them. So this is a D8 trisection of S1 cross S3. This is a D6 trisection of S1 cross S3. This is a D6 trisection of S4. That's a D2 trisection of S2 cross S2. There's probably, there's one where you just take the connect sum of the CP2s and you map them around. But there's maybe, I don't know, 6 or 7 of these things. And they're basically all on the board or variations. And we were able to prove that these are the only trisections that have, for example, a genus 2 trisections where the group has an element of order greater than 2. But the Z2 cross Z2 case is a little bit funny. We were never really able to pin down a classification in that case. So we almost did a classification of genus 2 trisections, but it got a little out of control. So, all right, I think I'll stop. Thank you for your attention.